Um, Good afternoon. Welcome to the second video of the probability theory. And in this video, I will talk about probability measure. And for the first video, I talked already about uh, the sigma algebra, the sigma field on omega. So the second definition, the definition 1.2 here, let F be a sigma field on omega. It means that we start from a sigma field on the sample set omega, then a probability measure that we denoted by P is a function or a mapping that map from a sigma field F to the real interval 0, 1. But it's not just a simple mapping. We can call this mapping a probability measure if it is satisfy these two conditions. So the first condition is that P of omega equal to 1. And the second condition is that P of the union of the subset, pairwise disjoint subset of F equal to the series of the P of all pairwise disjoint set. So in this case, if we have A1, A2, so on, a pairwise disjoint set of F, then P of A1 union A2 union so on is equal to PA1 plus PA2 plus dot dot dot. So this is an important condition that, and also difficult to prove sometimes. And in the first video, I mentioned already about the probability space that we denoted by omega fp. And uh, just just remind that omega fp is a probability space, and the sigma field f here, it is the set of all events. It means that it is the sigma field f, it contains all the subset of omega. So we call it the set of events. And I also provide you an example about probability measure. So we still start from, the same experiment as in the first video about flipping a coin for one time. And the sample set that we get here is, has two elements, H and T. And in the first video, I tell you already that the power set of omega is the biggest sigma algebra or biggest sigma field on omega. And in this example, I assign a mapping P from F to the real interval 0, 1. And this is the mapping P, that P of empty set equal to 0. P of the set of H equal to 0.5, P of the set of T equal to 0.5, and P of omega equal to 1. And in this example, I will show that P is a probability measure. So because P maps from F to 0, 1, and we want to check if it is a probability measure, we have to check two conditions of this definition, of definition 1.2. So the first condition is that P of omega equal to 1. So obviously from this assignment, okay, sorry. From this assignment, we see that P of omega is equal to 1. Okay, so the first condition is satisfied. The second condition, we have to check that if A1, A2, so on are pairwise disjoint subset of F, it means that A1, A2, and so on are belong to F, are element of F, and we will prove the P of the infinitely union of AI is equal to the series of P of AI. we have to prove this equality. If our mapping P satisfy this equality, then we can say that P is a probability measure. And in this case, because P is a mapping that map from F to 0, 1, it means that the domain of the mapping P is F. And from our example, the set F has four elements: empty set, H, T, and omega. So to prove this equality, we have to check for the union of AI equal to those four elements of F. So in the first case, if the union of AI equal to empty set, so in this case we check if it is satisfied, I mean the value of the left hand side equal to the value of the right hand side or not. So from the pairwise disjoint of AI, if this union equal to empty set, we can imply that each AI equal to empty set for all I belong to M. If AI are not pairwise disjoint subset of F, we cannot derive this. We cannot derive this, we cannot get it. So in this case, uh, P of the union of AI is equal to P of empty set because union equal to empty set. And from the above assignment, from our example, we said P of empty set equal to 0. So if P of empty set equal to 0, it means that this one, the left hand side of this equality equal to 0. And for the right hand side of this equality is that the series, the summation I equal 1 to infinity of P of AI is equal to summation I equal to 1 up to infinity of P of uh, empty set, because each AI equal to empty set. And then because P of empty set equals 0, then the right hand side of this equality also equal to 0. And we see that it is these are equal. So the first case is satisfied. Now we go to the second case. Because F has element H and T and omega. So for H and T, the proof is similar. That it follow the same fashion. So I prove only one case. So this, in this case, the union of AI equal to the set of H. Then from the pairwise disjoint of AI, we can derive that there exists a set AK equal to the set of H, and the rest are equal to empty set. So from this consequence, we can get the left hand side of the equality, that P of the union equal to P of H equal to 0.5. 0.5 is from our example. And the right hand side, the summation from I equal to 1 to infinity P of AI is also equal to 0 plus dot 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 plus P of the set of H plus 0 plus dot 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 equal to 0.5. And this is in the position, in the K position, because there exists AK equal to the set of H and the rest are empty set. That's why we get this. And for the case that union equal to the set of T, it's similar to this case. So I go further to indicate that the union is equal to omega. So in this case, we divide it into two subcases. So the first subcases is there exists AK equal to the set of H and AL equal to the set of T. Why we can do that? Because AI are pairwise disjoint, and in the case that the union equal to omega, we know that AK and AL, we know that H, the set of H and the set of T are also belong to us. And when we, when we take union of the set of H and union of the set of T, we will get omega. This is the possible case that can be happen in the case of union equal to omega. So, and the rest are equal to empty set. Then the left hand side, P of the union equal to P of AK union of AL, because only these two sets that are not empty and the rest are empty set. So it's equal to P of omega, which is equal to 1 from our assignment. And the left hand side, the summation I equal to 1 to infinity of AI equal to 0 plus dot 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 plus P of H in the K position, because we have AK equal to the set of H, and plus dot 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 plus P of the set of T in the L position, because we have AL equal to the set of T, and plus 0, so on. Then we get the value of this equal to 0.5 plus 0.5, which is equal to 1. And we see that the value of the left hand side and the right hand side of equality are equal. So it is satisfied the second condition for the sub case, for the first sub case. And another sub case is that if we have the union I equal 1 to infinity of AI equal to omega, then there is AK equal to omega, and the rest are empty set. So in this case, it's similar to the previous case that we can derive P of the union equal to P of omega equal to 1, and the summation P of AI also equal to 1. And because the mapping P satisfy both conditions of the definition 1.2, so we can say that P is a probability measure. If it not satisfy one of the two conditions, we cannot say that P is a probability measure. Okay. Thank you, and see you in the next video.